introduction, and then we can start.
Okay, sure. So I'll just check, you can see just the slide or not the presentation mode with the next slide?
Yeah, no, we only see the one slide.
Perfect, great, thank you.
And it's ready, Bruce.
Okay. So good morning, good afternoon, and good night, depending on the place that you are. So today we have the pleasure to have Dr. Tessa Charles from the University of Liverpool. Well, she's original from Australia. A little about her. She got her double bachelor degree in 2011, one in science, in physics, another engineer with honors. And in 2016, he got his PhD from the University of Monash in Melbourne, Australia. And from then, from 2017 to 2020, he was working at CERN. He was working in the FCC, working in strategy for optic correction for low emittance. From the last year, for 2020, she is a lecturer in University of Liverpool. She is basically established a accelerator research group studying emittance tuning and correction methods, and she still continue collaborating with CERN. She has several talks in international conference like IPAC. Also, she is author of several papers. She also already gets several grants and scholarships and so on. And without further introduction, I'm going to welcome to Dr. Tessa Charles, who today will talk nonlinear beam dynamics involving current, spike, and beam shaping. Dr. Tessa?
Okay, thank you very much for that very kind introduction. Okay, so yeah, I will talk about this nonlinear beam dynamics, specifically when current spikes appear and how we can use that to shape the beam in different ways. And specifically, when I'm talking about when current spikes appear, it's usually when we have this phenomenon called caustics appearing. So I'll start, oops, if I can go to the next slide. There we are. So just describe what caustics are in case anyone is not so familiar with the term. An ordinary coffee cup provides a very good example of caustics. So in a coffee cup, many rays of light come into the cup and are reflected off that curved surface, and those reflected rays form those bright lines that you can see in the photo on the left and highlighted by the red line on the right. So that cartoid shape is formed from the caustic lines. And that's because the caustics are an envelope of those reflected trajectories where the light intensity is greatly enhanced. And another example of caustics is the dancing network of lines that you see on the bottom of a lake or a pool on a sunny day. So hopefully that's coming across on Zoom okay, that sort of video. If it's not, I'm sure you've all seen that effect before. And this is often called natural focusing because it is a unintended yet mathematically stable production of these bright lines of light. And in fact, caustics in optics, in ordinary light optics, you can see all over the place. So sort of once you know what they are, I'm sure you start seeing them everywhere. I know I certainly do. And so caustics are very easily recognizable in light optics. And in electron microscopy, they're also well understood and utilized in electron microscopy, but it was only relatively recently that a few of us are starting to look at how caustics can appear in particle accelerators. So in this talk, I will continue to introduce some of these concepts surrounding caustics, and then I will go into how we can actually use caustics. So I've got a few examples of the usefulness of caustics, and then tucked in the middle there, I'll share some experimental results that we took at Max 4 a couple of years ago. So just like in light optics, we do see caustics in accelerator physics, but instead of rays of light, we have electron trajectories. And instead of reflection and refraction, we have things such as longitudinal dispersion in a bunch compressor, for example. So this plot here shows a number of trajectories passing through a bunch compressor. You can tell it's a bunch compressor because the bunch length Z is getting smaller towards the end of the compressor here. And if I zoom in at the end of the compressor, you can see actually the trajectories are starting to coalesce at the head and tail of the bunch, so the extreme values of Z. So this is not dissimilar to the optical caustics example from the very start. And we can calculate the density of the trajectories or the rays of light in both cases. And you can see that at the position of the caustic, we see this sharp spike in the intensity, and then that drops off very rapidly as we move away from the caustic. So that is to say that at the position of the caustic, we have greatly enhanced light intensity or charge density, depending upon which example we're looking at. So in other words, where there are caustics, in the accelerator example, there will be current spikes. And this is because caustics are a singularity in the density of a family of trajectories, which is what's on the slide there. Singularity in the density of a family of trajectories. So this is not merely particle tracking. So you might be fooled for thinking that on the previous slide, because we just tracked the particles and saw the result, but you'll see this caustic analysis is not merely particle tracking, and it's not merely 1D longitudinal dynamics either. This is because these effects do not reside in single trajectories. Instead, we need to consider what I refer to here as a family of trajectories, and that way we can investigate properties that reside within those families of trajectories, so things such as focusing within a single bunch. So caustics, the singularity in the family of density of trajectories, they are a many-to-one mapping that result in a pile-up of particles at specific locations. And these caustics, which result in current spikes, are a catastrophe in the mathematical sense of the word. So meaning that caustics fall into catastrophe theory. So this figure here demonstrates some of the key features of catastrophe theory. So namely that small continuous perturbations in one parameter can result in very large changes in another parameter. So for example, if I was to walk along this top surface here in the direction of negative x, at one point when I take one more step, I'd fall off the edge of that cliff and see a large change there in z. And if I was to take this curved sheet of paper and project it onto the XY plane, then this red line here maps out the peak projected density. And this has a name, it's called the bifurcation set, and I'll refer to that again later on. And then finally, if I was to take this curved surface and take a slice through it at one location in Y, then you'd see this S shape here. And if you're like me and happen to have spent a lot of time thinking about strong bunch compressors, then this might just remind you of the longitudinal phase space shape at the end of a strong bunch compressor. So here is the longitudinal phase space distribution as it evolves through a bunch compressor. So this is just a standard 4-dipole chicane. And you can see the bunch is being compressed because the horizontal axis is actually changing. So the bunch is being compressed. And by the end of the compressor there, you can see this backwards S shape is just starting to form. And so I'll, just in case, because I know there's probably a mixture of people in the audience and watching the video with a range of different backgrounds. So I'll just take a brief aside here to explain how a bunch compressor works for anyone who's not so familiar with it. And so in a typical bunch compressor, what we need is to take a chirped bunch. And what I mean by that is we introduce this correlation with energy and position along the length of the bunch, and we call this a chirped bunch. So in this case, the tail of the bunch has a greater energy and the head of the bunch has a lower energy. And then when we send this bunch through the chicane, we are going to split up the particles by energy. We introduce that dispersion, and the higher energy particles will take a shorter bunch length through the chicane. The lower energy particles, trajectories can be bent more easily, will take a longer path length through the chicane. And then we'll see this rotation in the longitudinal phase space. So essentially allowing the tail to catch up with the head, so to speak, and compressing the bunch longitudinally. So I said we introduced the chirp. The way we actually do this, to take a step back in the accelerator, we do this by accelerating off crest in our accelerating structures. And so that way we're going to give one end of our bunch a higher energy and the other end of our bunch the lower energy. And this is a somewhat simplified view, aside from the fact that it's just made up of these sort of cartoon images. This simplifies things quite a lot because what I've described here is essentially what's happening to first order. But of course, there are going to be some higher order effects. And so in reality, there is another step here, because when we do accelerate off crest on our RF curve, the bunch will pick up the curvature from the RF. So we end up with a bunch that looks something a little bit more like this. And so then one common approach is to then add a harmonic cavity, which is usually the third or fourth harmonic of the main RF frequency. By adding those two frequencies together, we end up with a result that looks much more linear. Okay, so moving back again to the slightly more realistic simulation results. Oh, in fact, sort of not yet, just before I do that. So this is, if this is our LINAC for an FEL, then here are all those components again. So often there are at least two bunch compressors. Here we have two chicanes. We have the injector, and then this red box here is that harmonic cavity. So just as shown before, we have that curved longitudinal phase-space distribution, which we then linearize with the harmonic cavity, then send it through a bunch compressor, so we end up with a very short bunch length, ideally. And so we use our standard transport matrices from accelerator physics. Again, just to first order, that would look something like this when we're looking at the final longitudinal position. All of the other terms equal 0 usually, or close to 0. And in fact, R11 in, say, a 4-dipole chicane is often equal to 1. So really, it's just R56 is what's characterizing our bunch compressor. And the value of R56, when considered with the angle of our chirp, is what we use to determine to what degree we can compress our bunch longitudinally. But again, we need to actually consider these higher order effects because they do have quite a predominant role in many bunch compressors, particularly strong bunch compressors. So we can expand this approach using a Taylor series expansion and then add a few more terms onto our expression here as well. So we have the major parameters of interest are R56, T566, and U566, and they're the first, second, and third order longitudinal dispersion. So you'll probably hear me say those names quite a few times throughout the rest of this talk. Okay, so now moving back to the simulation, particle tracking simulation results. And so I mentioned that at the end of the compressor here, we have this curvature appearing, this backwards S shape is starting to form. And so if I take this distribution here and calculate the associated current profile, this is what we see. So we see a current spike at the head and at the tail of the bunch. And this is problematic because these current spikes are basically they're beacons of CSR, coherent synchrotron radiation, and this CSR threatens to degrade our emittance. And the way it does that is because we have a very short bunch length, typically if our application is for an FEL, but even if it's for a linear collider, and in any case when we have a short bunch length, that bunch can radiate coherently. If the bunch length is longer, then it will just radiate incoherently. But if we have a short bunch length, it will radiate coherently when that particle goes through a dipole, so goes through a bend. So in this diagram here on the slide here, we've got a bunch, which is this blue oval here. It emits CSR, and because the CSR can travel in a straight line, it travels in a tangent to the path of the electrons, and the electrons take this curved trajectory, which is just a little bit more bent. It means that radiation from the tail of the bunch can cut the corner through the dipole and interact with the head of the bunch. So that means we have energy from the tail of the bunch being lost and given to the head of the bunch. And that's what's being shown in the plot on the right here. So this is the change in energy plotted for a bunch just for 3 different dipoles, but you can see the shape is the same. So if you just look at the magnitude, you can see that the energy is being redistributed from the tail of the bunch to the head of the bunch. And the reason why this is problematic for us, or why it leads to CSR growth, is because we have particles at different locations longitudinally along the bunch will receive or lose a different amount of energy. And so that's going to result in a kick in X or X prime because this is happening in a dispersive region. So this change in energy causes a kick in X or X prime. And so that means that the longitudinal slices can be offset as shown sort of in the bottom left corner of this slide. So as you can see here, different slices are being offset, and that means that our overall projected emittance becomes larger. So the emittance of any one of those slices remains small, as you can see, for example, the blue or the green ellipse, but the overall projected emittance is much larger. So this is the way that CSR can enlarge our emittance, which of course is not ideal. And I mentioned that the current spikes, there we are, the current spikes in particular can produce a lot of CSR. And that is because this expression, which is the same expression from the previous slide, this expression tells us that the rate of change of energy due to CSR is proportional to the derivative of lambda, which is the linear charge density. So where we have a linear charge density that has these sharp spikes, any function where we have a sharp spike and then take the derivative of that, it means we're going to have a very strong CSR effect. So this is why we care about these current spikes, particularly in FELs. There's something we very much would like to avoid in order to preserve our emittance. So a number of years ago now, myself and a few colleagues, we derived this caustic expression, and it tells us where and under what conditions these caustics will form. So where being what values of Z sub C, what value of the longitudinal position, and so under what conditions, meaning what values of R56, T566, and U566, which again are the first, second, and third order longitudinal dispersions. And then the other parameter left in this equation here is delta as a function of Zi. So that is the initial longitudinal phase space distribution shape. So here's a typical initial phase space distribution for a bunch entering a bunch compressor. So it's got that strong chirp that you can see there. And we can describe this with a cubic fit. And we do this very intentionally, despite the fact that it looks incredibly linear. We fit it with a cubic because it's these very small deviations away from linear that can end up resulting in these current spikes forming. And this is not surprising, given that this fits into catastrophe theory, because we know that in catastrophe theory, it can be these very gentle perturbations that result in a dramatic rise in the peak current. So here's that caustic expression plotted for a chicane or a compressor of variable R56 value. And I can overlay on top of this plot a number of individually calculated trajectories. So when I do that, you can see here that the caustic expression, it's mapping out the envelope of those trajectories as we expect. And the shape might almost seem familiar because it's the same shape as that bifurcation set from this catastrophe figure a few slides earlier. And we can consider just a particular value of R56. So say if we have a compressor of negative 10 millimeters, and if we calculate the density of trajectories along that line, then again, we can see these current spikes at the head and tail of the bunch. So where we are crossing the caustic line is where we see the current spike forming. And so what we can now do is start to change the values of T566 and U566 that were also in that expression. So when we do this, we can see these caustic lines start to morph and shift and change. And here I've shown 3 different examples just with different values of T566 and U566. And on the lower half of the slide, we've got the corresponding particle tracking results and essentially current profiles. And I've also pointed to 3 examples of where such scenarios can be seen sort of out in the real world at real accelerators. And so these 3 structurally stable motifs can be described, the taxonomy of them can be described in the work of Tom. And in this case, we have a fold, a cusp, and a butterfly catastrophe. And so it's the name of the catastrophes. I will point out, though, that in most cases, for our applications, these are just names, and we actually don't need to know what class of catastrophe we're dealing with entering into a scenario, because each of these equations was arrived at with the same expression, the expression that's on the slide again here. So we just changed the values of the control variables to arrive at 3 different types of catastrophe. And here I've just zoomed in on the third one, that butterfly catastrophe, just so you can see that it's really quite intricate in the way that it sort of is folding in and around on itself. And this gives us an indication of how we might be able to sculpt the electron trajectories to our benefit. So if we wanted a current profile of a particular shape, this gives us a bit of an idea about how we might achieve that. And so I'll move in now to the first example of how we can use this caustic nature, and that is through shaping the current profile, in particular trying to suppress the current horns. So I mentioned that these current horns, they're bad news for FELs, and this is probably best illustrated through the experience at LCLS. So in this paper by Yuan Tao Ding and others from a number of years ago, they showed that if they just collimate away these head and tail current spikes, they can increase the FEL power from about 3.5 millijoules up to 4 or 5 millijoules. Not only that, they reduce the energy spread and get much more even lasing of their bunch. So it's worth understanding what actually drives this current spike formation. So here is an S-band LINAC, which I'll consider in this example of that I'm about to go into detail with. So in this S-band LINAC, with particle tracking results at the end of LINAC 2, we end up with this longitudinal phase space distribution and associated current profile. So clearly exhibiting this current spike at the head and tail of the bunch, sometimes called current horns. And so along with the caustic expression from earlier, we also derived this caustic condition, which identifies the regions between where caustics of different codimension exist. And what I mean by that is in the dark blue region, for example, that's where we expect 2 current spikes, one at the head and one at the tail of the bunch. In the light blue regions is where we expect a single current spike to the head or to the tail of the bunch. And in the white region at the end there is where we expect no current spikes to form, so no caustic formation, and we expect a relatively uniform current profile. And the point A in this plot here is actually the working point of the S-band LINAC example from the previous slide. So right in the middle of double current horn territory, and that's what we saw with that we had a current spike to the head and tail of the bunch. So we'd prefer to be in this white region. So in other words, we need to change the value of U566 from close to 0 out to about 2.5 or 3 meters or so to get us sort of well into this non-caustic region. And so we can do this through adding an octopole to one of our bunch compressors. So an octopole placed in a dispersive region will vary U566 in a similar way that a sextupole in a dispersive region will vary T566. So a sextupole in a dispersive region will change the second order longitudinal dispersion, and an octopole in a dispersive region will change the third order longitudinal dispersion. So we can do this. We can add an octopole to our low energy compressor. Here's just showing the optics through those 2 compressors and how we could vary the U566 even with a sort of a hesitant to say, but a relatively weak octopole. It was not too strong of an octopole, which is nice. And then I'll show you the results of what happens when we do that. So this is a situation that we started without the octopole, and then just through adding the octopole, we essentially set up conditions under which these caustics can now no longer form. So we've modified the optics so the caustics can no longer form, and you can see we've largely suppressed the current horns from forming. And so we started with a normalized horizontal projected emittance of 1.359 millimeter millirad. And after suppressing the current spikes, we've limited that CSR-induced emittance growth, and so now the emittance is 0.76 millimeter millirad. So it's a 63% reduction in the CSR-induced emittance growth. And here I'm just showing the slice properties of a number of parameters at the end of LINAC 2 here, so basically at the end of the LINAC. And so you can see that the slice emittance for X and Y doesn't change much between these two examples of before and after the octopole was added. The main change comes in when we look at the X centroid position. So essentially, without the octopole, the CSR effect was offsetting the various slices along the length of the bunch. And then when we add the octopole, the CSR effect is reduced. And so those offsets in X are also much reduced. And so our projected emittance remains much smaller. Okay, so everything I've shown you to now has been simulations. So it's nice to see some real experimental results as well to make sure that this isn't some just weird simulation thing. We do actually see this in the real world. So a few years ago, in pre-pandemic times, we went to Max 4 and took some measurements on their LINAC. So Max 4, it's located in beautiful Lund in Sweden, and they have a 300-meter long LINAC, S-band LINAC, which serves as an injector into two storage rings, one at 1.5 GeV, the other at 3 GeV, and also supplies a short pulse facility. So here is the LINAC in a little more detail. They have two guns, actually, a thermionic gun, which is used for the top-up injection of the two storage rings, and a photocathode gun, which is what we used in the experimental results I'm about to show you. They have two bunch compressors, and the bunch compressors are actually a very neat design. So they're this dog leg shape here, and they're a positive R56 compressor. And the thing that I think is just so neat and clever about them is that the value of T566 of the compressor is actually very close to the T566 value that would be needed to linearize the longitudinal phase space shape. So I mentioned earlier that often a harmonic cavity is used to linearize the longitudinal phase space distribution. In this case, they don't have that. Instead, they just have a purely optical solution. And the way it's set up is they essentially don't need any additional elements in order to linearize the longitudinal phase space. And so because of this, it's sometimes called self-linearizing. They do have in their compressor, though, two sextupoles, which are included in order to basically fine-tune the T566 value, because it's not the perfect T566 value to linearize the longitudinal phase space. It's just really quite close, and then they can fine-tune that value with T566. Sorry, fine-tune that value with the sextupoles. And this was really great for us because it meant that this also means that we could vary the value of T566 and see how the caustics change, making this really a perfect testbed for studying caustics. So we did just that. We varied the sextupole strengths in the low energy compressor there. Then we accelerated the bunch far off crest in the main LINAC. So essentially introducing a strong correlation with energy and position along the length of the bunch. Then we placed a screen after the first dipole in BC2. And we did this in order to basically to get an indication of the longitudinal current profile. So here's just an example of one measurement there. So essentially using that first dipole, basically like an energy spectrometer. And so when we did this, here's a series of data that we took. When we varied the sextupole strength, we could see that the current spike shifted from the head to the tail of the bunch. And this is what we hoped would happen. So as we changed the tip value of T566, the current spike shifts from the head to the tail of the bunch. And then from this, we really wanted to extract these caustic lines. And so we needed to basically find this value of Z sub C. So this caustic expression here, this set of parametric expressions, is the same one as from a number of slides earlier. We've just rearranged it a bit so it looks a little different, but it's the same expression, it's equivalent. So we can extract this value of Z sub C. It's defined as being the position from the current peak to the origin on this plot here. So this plot here is showing a number of longitudinal phase space distributions, very much simplified just for illustrative purposes. But the origin on this plot here is essentially the middle of the bunch before it entered the bunch compressor. So it's not straightforward really to extract it from those current profile measurements, but we can try. So essentially the way we calculated this value of Z sub C is basically the position from the current spike to where we reached where the accumulated integrated charge equaled half the total charge when integrating from one end of the bunch across. So this approach is accurate for the blue and the orange and the green curves. For the red curve, it starts to become less accurate because you can see one end of the bunch here is crossing over the origin on this plot here. So it starts to become a little bit less accurate. But nevertheless, it gives us a good indication. So when we do this, this was essentially the result that we got. So the red line here is the caustic line, and the blue dots are obviously our experimental data. So there's a clear systematic offset that you can see there. If I just remove the offset, then you can see the two do agree quite well in shape, but this offset is a little unfortunate. And this offset is basically appears because the experiment we're performing is far from perfect. That accelerating really far off crest in the main linac to get an indication of the longitudinal distribution is not a perfect measurement. I should say though that the good news is that Max4 is actually installing a transverse deflecting cavity, which would allow us to much more accurately measure the longitudinal current profile. And so hopefully we will be able to redo this measurement at some stage and see that offset removed. But the reason for this offset is two reasons. One is that we were encountering wake field the whole way through that main linac, which is really unavoidable. And the second reason, which was the predominant reason, is that we were taking a longitudinal phase-space distribution which was curved, essentially a C-shaped longitudinal phase-space distribution, and projecting that onto the transverse plane. So we have a phase-space distribution that's multi-valued in energy. So at any sort of Z position, we've got two values of energy, and then sending that through a dipole and measuring it on the transverse plane. So it's going to artificially elongate the bunch length measurement, resulting in this offset. But having said all that, I'm worried that might sound a little bit negative because we were actually thrilled with this result. This is much closer than we thought it would be. The fact that we got anything close was a really great result. And then, as I said, hopefully we can repeat this measurement with a transverse deflecting cavity, which would be much more accurate, and hopefully see these two come into alignment. One thing I'll just note is that the compressor in the Max4 linac is compressing to a very large degree. As I said, it's applying a short pulse facility, so they're really going for femtosecond bunches. And given that we're compressing to such a short degree, it's difficult to even measure the bunch length of these very short bunches. So one nice thing about the caustics is we can see that in between these two red lines here, there's actually a region of T566 where the caustic line is undefined. So there is a gap between these two red lines. And what that means is essentially that we're compressing to a very large degree and the current profile is relatively uniform. So we don't have a current spike, or if we do, the current spike is in the middle of the bunch, which is where we want to be. So we can also use this as a way to characterize the bunch compressor to make sure that we're working at the optimal working point in order to compress to as large a degree as we can. Okay, so I'll move on now to a completely different application, which is looking at how we can use the information that caustics give us to look at the longitudinal phase space manipulation and management in recirculating machines. So this is work I did with Dave Douglas and Peter Williams, and we considered here this recirculating UK FEL concept. It's a recirculating and energy recovery machine that has many arcs, so 8 loops on the way up as we're increasing energy, and then passes back again 8 times on the way down as we try to recover the energy. And so we could, for each of these arcs, again, we could plot these exclusion plots to work out perhaps what our values of R56 and T566 should be for each of these arcs. And so we can do this, as I say, for every arc. The result of the previous arc feeds into the next arc. I won't go through all of them. I'll just jump to the last one here. Hopefully you can see on the slide there, this black dot here, that's the working point in our example. And so you can see at the final arc here, we've put our working point right up to the edge of the boundary between the different caustic regions. And that's because in that last compressor, we're trying to compress the bunch because this application, again, was for an FEL. So here's the distribution at various locations. So from the gun, we have this distribution here. Then as we accelerate up to the end of the final arc 8, after we've compressed the bunch, we end up with this distribution. And then after the bunch lasers, we see the middle portion of that bunch is smeared in energy as it lasers, and now we have a distribution with 3 lobes. And this is the distribution that we then try to energy recover. So then we do the same thing on the way back down in energy, which is a much trickier thing really to try to come up with solutions for in terms of the longitudinal phase space management. So you can see here again, we do the same thing to every arc. We actually found we needed to cross over into the caustic region for one of the arcs, and then we came straight back out again. What we were doing there is we're actually over compressing the bunch, and we found that was necessary in order to stay in the non-caustic region for the majority of the time. And then finally, at the end of passing through all those arcs, we can get the energy down to 4.8 MeV. And again, you can still just see these 3 lobes of the longitudinal phase space distribution. It's always got 3 tails. So this applying the caustic approach in this way is really a way to sort of pare down the viable parameter space from something that was really intimidatingly large to something that's much more manageable. And so just looking at the time, okay, it's good for time. So I'll just mention the last application that I was going to refer to, and that's looking at microbunching instability. And this at the moment is my favorite application, because microbunching instability results in a series of current spikes in a bunch. So microbunching always involves current spikes, and as I've said many times now, caustics always result in current spikes. So then we thought to ask the question of, is microbunching then a caustic phenomenon? And the answer is yes, it is. So we went through a similar approach and derived a set of caustic expressions for microbunching instability. And this is what we ended up with. So this is essentially microbunching seen from a caustic perspective. So each one of these red lines is a caustic line. So it's not a trajectory, it's a caustic. And so just to remind you, that means it's basically identifying the regions where these families of trajectories are starting to pile up and where we will experience current spikes. And so here we can see wherever we're crossing one of these red lines, we'll see a current spike at different longitudinal positions in Z. And for a compressor, a variable R56 value. And so I can zoom in just at one section of the plot there. And when I do, you can see that these caustic lines, they're bifurcating in some places and they're crossing over each other in other places. So there's actually really quite a lot going on in this plot. And when the caustic lines bifurcate, it means the current peaks also bifurcate, which I find really quite interesting. So here on the bottom half of the slide here, I'm showing the current profile for various R56 values. So starting on the right here with the R56 value of -9 millimeters, so just off the edge of this top plot, we can see we have a current profile that has some current peaks, but there's more weakly undulating current peaks. And then as we increase the magnitude of R56, moving across to the left in this plot, when we get to an R56 of negative 9.5 millimeters, we essentially cross over this caustic threshold, and then these small current peaks turn into very large current spikes. And then as we continue to move to the left, increasing R56 magnitude again, so now up to about 10.5 millimeters, these current spikes again split, they bifurcate. And then we can see, again, as we move across, we can see how the current profile continues to evolve. So we go from something that's having small current peaks. As soon as we cross over that caustic threshold, they become very large current spikes, and then those current spikes split in two. And so this is what's going on in microbunching. One thing I didn't mention is that this top caustic plot here has T566 and U566 being set to 0. And that is rarely ever going to be the case. But we can include T566 and U566. And when we do that, this is what we start to get here. So in these plots, the grey line is with T566 and U566 equaling 0. And the red lines is what happens when we change T566 on the left and, oh, sorry, that should be U566 is negative 2 meters on the right. So you can see on the left, the caustic lines have started to fold over on themselves, kind of, and on the right, they're sort of starting to shear across each other, I guess you could say. And what's interesting about this is that you can see here that actually we end up having a situation where these caustic lines are forming an envelope of themselves. So it means, if you remember, each one of these caustic lines is an envelope of trajectories. And now we have an envelope of caustic lines. So we've got a caustic of caustics situation going on. And this is something that one of the co-authors on this work, David Paganin, gave the name hypercaustics. So this is what we're referring to as caustic of caustics. And this seems to appear quite readily in microbunching, particularly if you're compressing basically as much as you can, which is quite often the case if you want a very short bunch. And finally, in my almost last slide, the fact that microbunching is a caustic phenomenon also reveals to us why it's such a difficult thing to model. And that's because microbunching, because it's a caustic phenomenon, means that we're going to have very sharp current spikes. And when we are calculating the effect of CSR, we're taking the derivative, the numerical derivative of a sharp spiky function, and then we're convolving that with another function that also contains a singularity. So it's a numerically hazardous, there we are, I've got the text on the slide there to say the same thing, but it's a numerically very hazardous calculation to perform, basically due to the nature of the microbunching having this caustic underlying nature. But given that we know now that it is a caustic phenomenon, we're working on at the moment whether that can give us insight into how we might better model CSR when microbunching is involved. And here is sort of venturing a little into that work, basically showing that on the left here we can calculate the current profile for a bunch that has some spikes when microbunching is just starting to form. But then as soon as we reach this caustic region, the current profile, the blue line here, starts to break down a little bit, or it starts to really start to diverge from the particle tracking results, which is that binned orange histogram. However, we can easily identify the locations of these current spikes, and we're working at the moment to see if we can work out ways to better model the current profile. Okay, so to conclude, I've covered quite a lot of distance, I think, in this presentation. So we started with just going over what caustics are. Basically, they're being this phenomenon that we see all over the place in optics, and then showing how we actually also see them in accelerator physics as well. I mentioned that we can derive this expression that describes the caustics and how using that expression, we can arrive at catastrophes of different codimension, which have these different names of fold, cusp, and a butterfly catastrophe. Then I showed how we can use this, the caustic expression to identify regions where caustics won't exist. And so in the case of FELs, where we get a current spike at the head and tail of the bunch, we can actually create optics solutions which will suppress these current spikes, minimize the CSR-induced minutes growth. Then I also showed how we can use it in recirculating and energy recovery machines as a way to manage the longitudinal phase space solutions. Then also showed the experimental results from MAX4, which with the offset removed agree quite well, at least in shape, between the experimental results and the theoretical caustic expression. And then finally, I mentioned how caustics can also be used to describe microbunch instability, which becomes quite an intense picture when it's caustic plot there, but it does give us a lot of information as to how the current profile evolves with microbunch instability. Yeah, so that's everything I had to show. So thank you very much for listening, and I'm happy to take any questions if we have time for that.
Okay, thank you very much, Tessa. And if somebody have a question? Alex, please.
Thank you, Bruce. Thank you, Tessa. Very nice. I have maybe a silly question. So do you think you could use caustics, let's say, if you want to change the current pattern, could you use as a knob, like caustics, where you can change one of these parameters and then change the pattern of the current pattern of your machine?
Yeah. I mean, that's not a silly question at all. That's yeah. So in fact, on the slide here, you can see at one place we have basically a linearly ramped current profile to one end, pointing sort of to one side of the bunch, and then pointing to the other side of the bunch. And this is through just changing the value of T5/666, and that's essentially shifting the caustic line. And I mean, in this example here, it's one that they were also interested at Lund University because they do a lot of plasma accelerations where a linearly ramped current profile is the ideal current profile for a drive beam of laser plasma acceleration systems. So that's an example of exactly what you're talking about, basically using the caustics, so using the control parameters of the caustic, so T5/666, to create a current profile that we want, which in this case is a linearly ramped current profile. If you want something that's sort of a bit more sort of involved or more specific, then caustics might be able to help you. It kind of really depends on the application, but certainly if it involves a strong current peak, then caustics can really help guide you as to how you can create that specific current profile. Does that make sense? Or did that answer your question?
Yeah, that does. Thank you very much. Maybe just a quick other question. I don't know if you mentioned it before, but so do you have programmed any further experiments to cross-check this offset that you measure in MAX4?
Yeah, we have plans. Nothing scheduled so much in that we don't know which date we'll be able to go there yet, but this is all sort of, pandemic dependent. But we do have plans to do this. In fact, there's a PhD student starting in October who will sort of take away this work and sort of extend it much further. And I'm sure part of that will be redoing these experiments, hopefully with the transverse deflecting cavity that's been installed at the end of the MAX4 LINAC. And then we will sort of really have it will be a much nicer experiment with a transverse deflecting cavity with far less sort of approximations that we were having to use in the experimental results that we did take. So it's something I'm really looking forward to, actually, is trying to take some more experimental results.
Cool. Good luck.
Thanks.
Any other question? Okay, I have two questions. One of the person who left is in the arrangement of the Chicana that you show in the first slide. What will be the maximum dispersion in energy that you can achieve with such a kind of arrangement?
The first
In the
slides.
first ones.
Yeah, sorry, I'll make my way back there eventually. It's yeah, around about here. Oh, there we are. The maximum energy spread, is that the question?
Yeah.
Yeah. I mean, it's a good question. I'm not too sure what the maximum would be. It would depend a little bit on the compressor, partly because the larger the energy spread, the greater the transverse width that you're going to have right in the middle of the chicane. So if the energy spread is too large, then you're really spreading out your beam transversely to a large degree, potentially sort of running into the vacuum chamber. But if that was sort of included in your design, then perhaps that would be okay. I'm just trying to think, is there any other limitations? There probably are. In fact, the larger the yeah, in some sense, the larger the energy spread, the further off crest you have to go in the sections preceding the chicane, which is not a problem so much, but it means that the further away from the RF crest you are, so the less actual acceleration, increase in energy you're getting, and that's generally sort of one of the aims of a LINAC is to accelerate the beam. But it's so I'm sorry, I'm not giving you a really firm answer. In terms of like a value on what would be the maximum energy spread, I'm not too sure. But when it comes to designing a compressor, it's the combination of this energy spread and the R56, which is sort of what you need to take into account. And generally, you don't want the R56 value to be too large, just because that will mean stronger bending angles. To get a larger dispersion, you would need a larger bending angle, and a larger bending angle will probably end up meaning greater micromotion instability generally. So because you don't want your R56 too large, it's generally sort of compensated with a larger energy spread. But there is a balance somewhere in the middle there. And yeah, if you were designing your own LINAC, it's just a sort of, I guess it'd be an optimization procedure to find out that optimum trade-off point.
Okay. And I have one more, maybe as Alex said, maybe it's a silly question, but this equation can also be applicable for protons, only for electrons?
Yeah, no, yeah, it absolutely can. I'm glad you said that actually, because yeah, I keep on talking about electrons because I always work with electrons, but it's totally applicable to protons as well. So all of these plots, with the caustic lines, which I'm just looking to see if I can jump to one. Basically here, if we've got, these are just particle trajectories, but they could be electrons or protons really. So it's, yeah, I should try to get out of the habit of always referring to them as electron trajectories, because this work is more general and could definitely be applied to any charged particle.
Okay. Somebody else have another question or comment? Okay, if it's not that the case, well, say thank you very much to Dr. Tessa, and I hope to have you soon. Yeah.
Great, thanks very much for having me.
Okay, thank you. And well, guys, see you in the next seminar. Thank you for coming.
Bye.